Hello and thank you for watching. My name is Astri Krasniji. Today we are covering CCNA Semester 2, Chapter 7, Routing Dynamically. Objectives for this lesson is to explain the basic operations of dynamic routing protocols, compare and contrast dynamic and static routing, determine which networks are available during the initial network discovery phase, define the different categories of routing protocols, describe the process by which distance vector routing protocols learn about other networks, identify the types of distance vector routing protocols. Then we'll configure RIP and RIPng or RIP new generation routing protocol, determine the route source, administrative distance and metric for a given route, and explain the concepts of parent-child relationship in dynamically built a routing table. The evolution of dynamic routing protocols. Dynamic routing protocols used in a network since the late 1980s. Newer version supports the communication based on IP version 6. We have dynamic routing protocols are divided into two. We have interior gateway protocol, IGPs, and exterior gateway routing protocols, EGPs. Now, interior gateway routing protocol is what we use inside our network. Exterior gateway when we want to communicate with a different network, with somebody else, with another autonomous system. Interior gateway protocols are separated into a distance vector routing protocols and link state routing protocols. Distance vector routing protocols, they learn routes by by what neighbor tells. They believe the neighbor. So they kind of like learn the route, how far it is, and what direction. While link state routing protocols, they want to build the map. It's like A to Z of the network, of the whole topology, before they make a decision how to send the packets to the remote network. Distance vector routing protocol, we have RIP and EIGRP to start with. These are like legacy protocols. They're not supported anymore, but they were startup protocols. The enhancement version of RIP, for example, would be RIP version 2. An enhanced version of EIGRP would be EIGRP, Enhanced Interior Gateway Routing Protocols. Link state protocols, we have two of them as well, OSPF and ISIS. These are interior gateway protocols. Exterior gateway protocols, we have path vector routing protocols, and only one, BGP. Purpose of dynamic routing protocols. Routing protocols are used to facilitate the exchange of routing information between routers. The purpose of dynamic routing protocols include discovery of remote networks. A remote network comes, it's available, the other routers, they need to discover about that network. And maintain up-to-date routing information. If the network is still available, if the network is not available anymore, all this information, they still need to be maintained in the memory. Choosing the best path to destination network. So if you find 2 or 3 ways to get to the destination network, it will find what's the best path to get there. And the last one, ability to find a new best path if the current path is no longer available. If the current path goes down, it's no longer available, you have to try and find out another alternative path. Main components of dynamic routing protocols include data structures. Routing protocols typically use tables or database for its operation. This information is kept in RAM. Routing protocol messages. Routing protocol use various types of messages to discover neighbors, routers, exchange routing information, and other tasks to learn and maintain accurate information. And then we have the algorithm. Routing protocols use algorithms for facilitating routing information for best path determinations. So purpose of dynamic routing protocols, here I have router 1 and router 2. First is routing protocol exchange messages. One of the most basic message is hello message. Like router 2 is saying to router 1, hello, I'm router 2. Routing protocols create and maintain data structures like database, which will keep the neighbor table, topology table, and so on. For example, router 2 will keep a neighbor table R2. R2 is my neighbor. Then R2 sends an update, says, okay, here's my network 192.168.1.0. Router 1 will add that into the topology table. This is a routing protocol maintaining data structures. After he got all different kind of networks on the table, on the topology table, it will run the routing algorithm to find out the best route, how to get to the destination the best way. Once it finds that, it will add it to the routing table. We can see that routing table by saying show IP route. Advantages of dynamic routing include, we have automatically share information about remote networks. Soon as one new network comes along, we automatically share that information. Determine the best path to each network and add this information to the routing table. Compared to static routing, dynamic routing protocol require less administrative overhead. You enable it once and you can forget about it. All the routing protocols will find out new routes, when they go, when they're not available anymore, when they are still available, and so on. Help the network administrator manage the time-consuming process of configuring and maintaining static route. Disadvantages of dynamic routing protocol will include that part of the router's resources are dedicated for protocol operations, including CPU time and network link bandwidth. So some of the CPU times and the network bandwidth is dedicated for the routing protocol, not for routing packets. Times when static routing is more appropriate. So if you can enable only static routing, there's no point to have a dynamic routing protocols. Dynamic routing protocols against static routing protocols. Advantages and disadvantages of static routing. So some of the advantages of static routing is easy to implement in a very small network. Very secure. Static routing is secure. No advertisements are sent as compared to dynamic routing protocols. Route destination is always the same, and no routing algorithm or update mechanism required. Therefore, extra CPU and RAM resources are not required. So we always know the path, how it's going to go from the source to destination. Disadvantages: suitable only for small topologies or for a special purpose such as default static route. Manual intervention is required to reroute the traffic. If some network goes down, we have to go to enable to have to configure statically and tell the router the network is down. Advantages and disadvantages of dynamic routing. So first we say advantages. Advantages is suitable in all topologies where multiple routers are required. So on the big networks, it's suited. Generally independent of the network size. Automatically adapts topology to reroute traffic if possible. So if you find another alternative path which is better cost or better metric, then it will reroute to that path. Disadvantages: can be more complex to implement. Less secure. Additional configuration settings are required to secure, because the dynamic routing is like very chatty. So if a router finds another router speaking the same language or same protocol, they will start exchanging informations. Sometimes we don't want that. So it's less secure. Maybe we can enable authentication to secure it, and so on. Route depends on the current topology and requires additional CPU and RAM and link bandwidth to keep these or maintain this routing information up to date. Dynamic routing protocol operation. In general, the operation of dynamic routing protocol can be described as follows. The router sends and receives routing messages on its interfaces. So like hello messages, update messages, request messages, acknowledgement, and so on. The router shares routing messages and routing information with other routers that are using the same routing protocol. If one router is using RIP, for example, routing protocol, and the other one is using OSPF routing protocol, they can't exchange the message. It's not the same protocol. So for the messages to be able to exchange, then they have to use both same routing protocol, like OSPF or RIP, both of them. Router exchange routing information to learn about remote networks. When a router detects a topology change, the routing protocol can advertise this change to other routers. So for example, I have router 1 here. Router 1 has got one connection, FA10 on the left, to network 172.16.10/24. Now, the router 1 is going to build a table. Network 172.16.10/24. Exit interface FA10. And the hops is 0. So if any packets or any data wants to go to that network, router 1 knows how to get to it. To get to network 172.16.1.0, I'll use interface FA1/0, and that's all, 0 hops, so it's directly connected with me. Let's go another connection, FA1/1 to network 10.1.12.0/24. Now this is how it's building the table. So as soon as you enable this interface with this IP address, the router 1 is going to build the table saying, okay, I know about network 10.1.12.0/24. It's going through FA1/1 and 0 hops. It's directly connected with me. So this router knows how to get to every network that is directly connected to. Now we bring router 2 in picture. Router 2 does the same thing. I've got connection through this network through interface FA2/1, and the network is 10.1.12.0/24. So I'm going to add that in my table. And exit interface FA2/1 and a hop 0. Router 2 has got another connection to another network through a other interface FA2/0, and the network is 10.1.23.0/24. So I'm going to add that to the table. Okay, that's a 0 hops away as well. So now the router 2 knows exactly how to get to every network that is directly connected to, but it doesn't know how to get to this network 172.16.1.0. That hasn't been advertised to router 2 as well yet. Now we're going to take a router. We have another router, router 3. The router 3 has got connection to the same network, share the network with the router 2, 10.1.23.0/24 through interface FA3.0, directly connected. So router 3 will add that on the table as well. And router 3 has got another network to 192.168.1.0/24, and exit interface for that network is FA3/1. So I will add that to the table. Now the networks here, every router knows about directly connected networks, but they don't know about the remote network. So at the moment the network is not converged. So to be converged, what they're going to do, they're going to share messages. So router 1, for example, is going to share the messages, is going to send updates to router 2. Both of his network is going to put them in the packet, ready to go to router 2. Once router 2 gets that packet, it will open the packet and it will see, okay, it's got 2 networks advertised, 172.16.1.0/24 and 10.1.12.0/24. You'll say, okay, well, I know about this network. I've got it here, directly connected. So I'm going to ignore that. So get rid of that. But this is a new network, so I don't know this. So I'm going to add this to my table. So it's going to put 172.16.1.0/24. How did I learn this network? Came from this interface. So to get to that network, I'm going to use that interface, FA2/1. And that's 1 hop away. Came from router 1, so it's 1 hop away. Now router 2 will make similar advertisement to router 1. So it's going to put all his networks on the packet and send them to router 1. Router 1 will open that packet and it will see in the packet there is 3 networks. It's going to compare these 3 networks with his own routing table, and it's going to see that 172.16.1.0/24 it already has it, and 10.1.12.0/24 it already has it as well. So it's going to ignore those 2 packets. So it's going to ignore that one, and it's going to ignore this one as well, 10.1.12. It says I already have it. There's no need for telling me this information. But I don't have the network 10.1.23.0, so I'm going to add this to my network table or routing table. It came from FA11, this update, so I'm going to add that as my exit interface. So FA1/1, and this is 1 hop away. So to get to router 2, it's 1 hop away. Now router 3 will do the similar advertising to router 2, router 3 to router 2. Router 2 is going to add this network that router 3 is advertising, 192.168.1.0 0/24, and it came on the interface FA2/0, and it's one hop away. Router 2 will advertise the networks to router 3. So router 3 is going to add the network 10.1.12.0, and it came on the interface FA30, one hop away. Router 2 will advertise to router 1 about the networks they already learned. The router 1 will ignore the networks they already has on the table, but it will add the new network, brand new network 192.168.1.0. He's learned it from this interface, FA11, so it's going to use that interface as the exit interface, and this network is 2 hops away. And router 2 will advertise to router 3 about the network that he's learned through router 1. So router 3 is going to add that to the table, so 172.16.1.0, this router, and it came on the interface FA3/0, and it's 2 hops away. Now you can see the network is converged. Every router knows how to get to every destination on the network, on the topology. So achieving convergence. The network is converged when all routers have a complete and accurate information about the entire network. Convergent time is the time it takes the router to share information, calculate the best path, and update the routing table. A network is not completely operable until the network has been converged. Convergent properties convergent properties include the speed of propagation of routing information and the calculation of optimal paths. The speed of propagation routers refers to the amount of time it takes for the router within the network to forward the routing information. Generally, the older protocols, such as RIP, are very slow or slow to converge, where modern networks or modern protocols, such as EIGRP or OSPF, they are very quick to converge. IGP and EGP, so interior gateway protocol and exterior gateway routing protocol. I want you to imagine this, that we have a network, that we have, say, 5 routers, router 1, router 2, router 3, router 4, and router 5. This is our business, our cloud. To other businesses in the world, we can represent ourselves with autonomous system number. Autonomous system number. This is the number that we buy, that we purchase to represent to other networks or to the internet. This is our business. So this is our AS number. Inside the AS number, we can run interior gateway protocols, IGP. Interior gateway protocols that we can use are RIP, EIGRP, OSPF, or ISIS. RIP version 2 we're talking about. So here we can choose which one do we want to use. Well, these protocols are within our autonomous system, so interior gateway protocol. Now imagine that our neighbor has a similar protocol. They have their own autonomous system number and their own interior gateway routing protocols. Now for us to communicate with each other, now we have to use exterior gateway protocols, EGP, which in this case we have only one, called BGP. So this is the difference between exterior gateway protocols and interior gateway protocols. Interior gateway protocols is what we run within our company. And we have few. We have RIP, EIGRP, OSPF. But when we want to talk our company with another company, it has to be through BGP. That's the only exterior gateway protocol available. So let's take another neighbor, autonomous system number. They have their own one. And when we connect with them, again, we connect them through exterior gateway protocol, which is BGP. This is how internet works. Company connected with another company through autonomous system numbers. Distance vector routing protocol, distance vector IPv4 IGP interior gateway protocols. We have RIP version 1. First generation is a legacy protocol, not supported. Well, it's supported in, still, but we have an enhanced version, which is RIP version 2. Simple distance vector routing protocol. Then we had IGRP. IGRP, first generation Cisco proprietary protocol, and it's obsolete anymore now because we have enhanced version, which is EIGRP, enhanced interior gateway routing protocol. So advanced version of distance vector routing protocol. These are distance vector protocol. With the distance vector protocol, what they learn, the neighbor will learn how far is the destination. For example, R1 is learning how far is this destination network or remote network, which is one hop in this case for RIP, and what direction, which way do I go to get to that network. So distance vector protocol uses routers as a signpost along the path to the final destination. While link state is different. Link state routing protocol is like having a complete map of the network topology. So the signposts along the way from the source to destination are not necessary, because all link state routers are using the identical map of the network. A link state router uses the link state information to create a topology map and select the best path to all destination network in the topology. So it's like getting the whole map, like A to Z, and then put yourself where you are in A to Z. That's your top of the tree, and to every destination you are calculating the best path how to get to the destination. Popular protocol is OSPF, or open shortest path first. So type of routing protocols, we have a class full routing protocols. These class full routing protocols do not send the subnet mask information in their routing updates. Class full routing protocols, we have only RIP version 1 and EIGRP, both obsolete. Created when network addresses were allocated based on classes, class A, B, or C. These cannot use variable length subnet masks and classless interdomain routing, CIDR. Creates a problem in discontinuous network, because if two networks you have, for example, 172.16.1.0/24 and another router has 172.16.2.0/24, when they advertise the neighbor router, they will advertise class full network 172.16, both of them. Now the third router will see it as not two separate network, will see it as one identical network, and it will do a load balancing, and that will cause a problem in discontinuous network. Classless routing protocol includes subnet mask information in the routing updates. These protocols, new protocols, RIP version 2, EIGRP, OSPF, and ISIS support classless routing protocol. Routing protocol characteristics. So we have a distance vector and link state. Remember, RIP version 1, version 2, IGRP, and EIGRP, they were all distance vector protocols. How far and direction. Link state, we had 2, OSPF and ISIS. They needed to build a whole topology, like A to Z map. Speed convergent. RIP version 1, 2, version 2, and IGRP are very slow to converge. EIGRP is fast. OSPF and ISIS, they are very fast to converge as well. Scalability or size of the network. RIP version 1, version 2, and IGRP, they like small networks, while the scalability for EIGRP, OSPF, and ISIS is large. Use of VLSM, now variable length subnet mask, or classless. Now RIP version 1 doesn't use classless, it's class full. Version 2 is classless, IGRP class full, and EIGRP, OSPF, and ISIS, yes, they use VLSM. Resources usage, they're very low on the first three protocols, RIP version 1, version 2, and IGRP. EIGRP medium usage of resources, while OSPF and ISIS high. Implementation and maintenance, very simple for RIP version 1, version 2, and IGRP are very simple. Implementation for EIGRP, OSPF, and ISIS is complex. Routing protocol metrics. A metric is a measurable value that is assigned by a routing protocol to different routes based on the usefulness of that route. Used to determine the overall cost of a path from source to destination. Overall cost. Routing protocol determine the best path based on the route with the lowest cost. Lowest cost, better. Routing protocol or RIP, routing information protocol, RIP, uses hop count. So on this network, I have router 1, router 2, and router 3. Router 1 is connected to router 2 and router 3. Through router 3, it's 64 kilobits per second. Router 1 to router 2, it's 1.544 megabits per second. Router 2 and router 3 is 1.54 Mbps. And the destination is from router 1 to 10.1.1.0/24. That's the destination. RIP will use a hop count. So as a packet travel, if they go directly to router 3, it will be 1 hop. If they go through router 1 to router 2, that's 1 hop. And then to router 3 is a second hop. So the RIP will see this as worse, because it has to go through 2 hops to get to the destination. If it go to router 3, it's only 1 hop. So it will use that. Even though it's a lot less the speed, RIP doesn't care. Looks at only hops, how many hops to the destination. OSPF, or Open Shortest Path First, will use a bandwidth, will add all the bandwidth from the source to destination. So bandwidth from R1 to R2 plus the bandwidth from R2 to R3, and it will compare to this bandwidth here, and it will choose a path with the best bandwidth. So you'll find out, okay, well, if I go through router 2, it's better bandwidth. Enhanced Interior Gateway Routing Protocol, EIGRP, will use bandwidth and delay by default, but they can use load and reliability as well. Like that, it will find that through router 2, it's got better bandwidth and delay. Distance vector technologies, distance vector routing protocols, they share the updates between the neighbors, not aware of the network topology, so they don't really know how the networks are really. It's just like they believe the neighbor, whatever the neighbor is telling them. Some send periodic updates to broadcast IP address, so RIP version 1 for example, and EIGRP will send a broadcast update to address 255.255.255.255, and even if topology has not changed. That's a problem if you send to this broadcast, because everybody will get it. All the devices, client machines, servers, switches, mobile devices, everybody's gonna get it. So it's very bad, because everybody's getting CPU is getting and the memory and the bandwidth is getting used for no reason. And all the updates that will go periodic, every 30 seconds for example, even nothing has changed. Updates consume bandwidth and network devices, CPU resources. RIP version 2 and EIGRP will use multicast address. EIGRP will only send an update when topology has changed. That's much more better improvement than RIP version 2 for example, or version 1, because the updates is only when there's something has changed, instead of just sending them periodic. Distance vector algorithm for RIP for example use the Bellman-Ford algorithm as its routing algorithm. IGRP and EIGRP use a diffusing update algorithm, or dual routing algorithm developed by Cisco. Routing Information Protocol, or RIP, routing updates broadcast every 30 seconds. Even if nothing has changed, they will be sent every 30 seconds. That's RIP version 1. Updates, version 1 and version 2 will send a UDP, so Unreliable Protocol, UDP, port 520. RIP new generation for IPv6 is based on RIP version 2 with 15 hop limit and the administrative distance of 120. Now RIP version 1, version 2 and RIPng, they all have administrative distance of 120. They'll all use 15 hop limitation, maximum 15 hops. So we have the characteristics and features, RIP version 1 and RIP version 2. Metric for both use a hop count as a simple metric. The maximum number of hops is 15. So a network with more than 15 routers between the source and destination network, not allowed in the RIP. Can't do it. So 15 is the maximum. Updates forward to address. Now RIP version 1 will forward all the updates to the broadcast address. Like we said earlier, all the devices on the network, they're gonna be hit with this update, and they're gonna read it up to layer 3 and find out that it's not for them. RIP version 2, it will multicast the updates to the multicast address 224.0.0.9. All RIP version 2 devices are configured to listen to this address for any updates. Support VLSM, variable length subnet mask. RIP version 1 doesn't support VLSM, version 2 does. Support of classless interdomain routing, version 1 no, version 2 does. Summarization, Version 1 doesn't support, version 2 does. Now summarization in RIP version 1 will summarize, but to the class full networks. So it will summarize, for example, if you have 10.1.1.0/24, it will summarize it all the class full address of 10.0.0.0/8. Supports authentication. RIP version 1 doesn't, version 2 does support authentication. Timers. RIP have some timers, so periodically sends an update every 30 seconds. This updates consist of broadcast of the entire routing table. So RIP, for example, RIP version 1 will send an update every 30 seconds, the whole routing table. Everything they have there will just send it there. Okay, version 2 doesn't send a broadcast, it sends a multicast, but still every 30 seconds and the whole routing table, everything that's in there. Now we have some timers. Update the time between each update interval. The value is set to 30 seconds by default, but it is configurable. The invalid timer specifies how long a routing entry can be in the routing table without being updated. This is set to 180 seconds by default. So, for example, if an update, I have an update now, and I don't have an update up to 180 seconds, I will still keep that route in my routing table. That is very slow to remove it. And flush down timer, flush down the timer after which a route is removed from the routing table. This is set to 240 seconds by default. After 240 seconds, it's gone. No more in the routing table. Hold down timer is a Cisco implementation. During this time, no update can be done to the routing entry. The default time is 180 seconds. Now, if you get an update in 30 seconds, then you don't hear an update for 3 minutes. And you put that route in invalid because you haven't heard that update, but if the packet wants to go to that network that's in an invalid state, the router will still send it. It will still send it there, even though you haven't heard an update, you haven't got an update for it. After this period, you will remove the route from the table, and you will not obviously send any more packets that way. Hold down timer is like, okay, well, if network goes down, then network goes back up, then it's like a flapping, going down and going up again, and it's changing states quite often. The Cisco says, okay, well, I'm not going to do any updates to that route for 180 seconds until I make sure that either the network is down or up. Route has split horizon. Split horizon is technique used to avoid routing loops. With split horizon, when a route is learned on an interface, that route is not advertised back on the same interface. So if you get an update from this interface going this way, now you're not going to send it back to the same interface. This analogy you can say, if I tell you a joke, don't tell me the joke back to me because it's not funny. Tell it to somebody else. Same goes with split horizon. If a router tells another router an update, doesn't accept it doesn't send the update back on the same interface. Split horizon with poison reverse. Split horizon with poison reverse is another technique used to avoid routing loop in split horizon with poison reverse. With this technique, router learned of an interface they are advertised back on the same interface, but they are poisoned, which means they have a metric of 16 unreachable. Then we have enhanced interior gateway routing protocols. This is bound triggered updates. It's bounded triggered updates. Only when device needs an update, when something has happened, network goes down or it goes up, then you send the triggered update. Use hello, a keep alive mechanism. So every 5 seconds, they say to each other hello, so they know that their neighbor is still alive in there. Maintains a topology table. So it keeps in topology all the networks that he's learning from the neighbors. Supports a rapid convergence. That's very important. Much more faster conversion than RIP. It is a multiple network layer protocol support. So it does support, like, for example, IP, different protocols, IPX, and so on. These are the characteristics and features. We have two protocols, EIGRP, legacy, we don't use anymore or not supported on many new Cisco devices, and EIGRP. Metric both use a composite metric consisting of bandwidth and delay. So they can use load and reliability if you configure it, but by default they just have a bandwidth and delay as a metric. Update forwarded to address. Well, EIGRP is same as RIP version 1. It does broadcast them to 255.255.255.255. EIGRP does multicast them to address 224.0.0.10. So it's multicast. Only EIGRP routers will listen to this address, or EIGRP protocol. Routers who understand the EIGRP protocol, they will listen to address 224.0.0.10. Supports VLSM. EIGRP doesn't. EIGRP does. Supports CIDR, classless inter-domain routing. No for EIGRP. EIGRP, yes. Summarization, no for EIGRP, yes for EIGRP, and authentication, no for EIGRP, and EIGRP does support authentication. You can see the enhancements in there. Okay, now I'm going to show you a demonstration. What we're going to do is build this network. Here the internet is going to be represented by a loopback 0 address. So what I'm going to do is I have a connection to R1 and R2. Let me move this up. So what I'm going to do is I'm going to start configuring R1 first. So first thing I need to do, go to global configuration mode, configure terminal. Once I'm in the global configuration mode, I need to access this fast Ethernet 00 interface first. So interface fast Ethernet 00 0/0. Give an IP address. So IP address version 4 is going to be 172.16.3.0. Oh, sorry, .1 in the end, /24. So IP address 172.16.3.1 and /24 is 255.255.255.0, and enable that interface. So no, shut down. Done. The next thing I'm going to do is I'm going to go to the global configuration mode and enable IPv6, because I'm going to configure with IPv6 as well. So IPv6 unicast routing. Right, once I enable IPv6, go back to the same interface, my interface FA00, IPv6 address 2001 db8 caf 1:1/64, and IPv6 another address for link local. So IP address FE80, that's my link local, ::1, and then finish it with link local. Okay, so end to go to the privilege mode, show IP interface brief. That says my fast Ethernet 00 has got an IP address and it's up on the states. So if I say show IPv6 interface brief, I can see the FA00 has got link local address and global unicast address, IPv6 address. Okay, and it's up layer 1 and layer 2 information as well. Now what I'm going to do is go to this serial interface. This is a DCE, so I need to configure the clocking as well and configure an IP address. This is serial 10, not 00, so 10, yeah. Okay, so configure terminal, interface serial 10, clock rate 64,000. So I don't forget that. Get that out of the way first. And then IP address is 10.1.1.1, and it's /30, so 255.255.255.252 /30. And then clock rate, done that, do no shutdown. Okay, we're done that, so we can go and confirm that. So end, show IP interface brief. Okay, so we can see the fast Ethernet is configured with an IP address and serial 10 is configured with an IP address. So now I'm going to go to do the similar configuration for R2. Well, before I do that, so I'm going to go to the same interface and configure this address as a version 6. So config T, You can see that interface gone down, the serial interface gone down because the other side is not configured. It will be down until I configure the other side. So interface serial 10, IPv6 address 2001, DB8, CAF 12, ::1, 64. And IPv6 again for link local, so IPv6 address FE80, ::1, and this is the link local address. Done. Router 1 is done. So I can confirm this. Show IPv6 address. Show IPv6 interface brief. I can see that serial 010 has got link local address and a unique IPv6 address. You can see the link local can be the same for both interfaces because link local is just on that local link here. It doesn't travel on this side, so it's within this link as well only. So go to router 2, show IP interface brief. You can see that there's no configuration on router 2, so first thing I'm going to do is access this interface FA01. So config T interface FA01 IP address 192.168.1.1 and /24, no shutdown. Exit, and then I need to do the interface on the serial interface. You can see the interface is gone up, so I need to do the serial interface. So interface serial 11, it's not 01, it's 11, enter. Give an IP address, our IP address 10.1.1.2 and /30, which ends up with 252. I'll do no shutdown. So both interfaces now, they should have an IP address and they should be up. So I'll go to end, show IP interface brief. You can see the fast Ethernet interface is 01 is up, layer 1 and layer 2 information is up, and the IP address, we have an IP address. Serial 11 has got an IP address 10.1.1.2 and it's up layer 1 and layer 2. Okay, good. What I'm going to do the next thing is go to router 1 and configure this internet interface. So that's going to be a loopback. Config T interface loopback 0, IP address say 200.1.1.1 0. Okay, /24. So no, don't need to do no shutdown here. So end, show IP interface brief. Okay, we can see that we have 00 configured, 10 configured, and the loopback is configured as well. Next thing I'm going to do is go to this PC1, and configure an IP address and the gateway and test I have a connection with the gateway. Same for PC2. Go to this address, this PC, configure with these addresses and ping the gateway. So first is PC1. So I'll go to PC1, open control panel, so start, control panel, network and internet, network and sharing, change adapter settings, properties. Select TCP IPv4, properties. Use the following address. So what I'm going to do here is 172.16.3.10 and 255.255.255.0, and the gateway is 172.16.3.1. Done. Open the command prompt, so cmd ipconfig to verify that we have that information. Okay, so I'm going to try and ping my gateway 172.16.3.1, and I have a reply. Okay, similar configuration I'm going to do to PC2. So go to PC2 now, click start, control panel, network and internet, network and sharing, change adapter settings. I'm going fast because I've gone through so many times. Properties, select IPv4 properties, and use the following IP address. So statically I'm going to configure 192.168.1.20, and the address is the same, 255.255. That's a subnet. and 192.168.1.2 is the gateway. I think that was the case, but this was a previous lesson. .2. Let me just check if I have configured .2 because I don't remember. No, .1. So I need to go back and change it. So config t interface FA01 IP address. I don't have to do no IP address. If I do the new one, it will remove the old one. And show IP interface brief. You can see that it has removed the old one and it's put the new one in. Excellent. So I go to router 2 again and press OK there. Close this. Open the command prompt to verify what we did. IP config. And I'll ping my gateway. So 192 ping 192.168.1.2. The gateway is replying. Excellent. Next thing I'm going to do is configure these interfaces, these IP addresses for the PCs. So go to PC1 first, and in the local area connection, go to properties, TCP/IP v6 properties, and I'm going to configure statically. So 2001 db8 CAF1::A. So 64, and the gateway is 2001 db8 CAF1::1. Now you need to go and check it out. So yep, that should be correct. Okay, so press OK, close. So if I do IP config, now this is my IP address. This is my IPv6 address that I configured. This is how I chose earlier. So you can see the IPv6 it can be more than one IP address, the temporary IPv6 address. So I can try and ping my gateway. So ping 2001 db8 CAF:1:1, and I've got a reply from my gateway. Okay, so the next thing is I'm going to do, coming back. Yep, it's coming back. Next thing I'm going to do is choose PC2 here, give it a IPv6 address, and try and ping the gateway. So go to PC2, right click, go to properties, select IPv6, and choose it obtain statically. So 2001 db8 CAF3, and what was the address here? The address was 14. Yeah. Okay. So 14 /64. So 2001 db8 CAF3::1. That's a gateway. I could use a FE80::1 as well. Same. Okay. So IP config. You can see the IPv6 address that we have is this one here. And that's our gateway. So I'll try and ping the gateway. So ping FE80::1. Did we configure IPv6? Show IPv6 interface brief. No, we didn't configure an IPv6 on the router 2, so that's what we're gonna do. We configure IPv6 on router 2. So router 2 config t interface FA01 IPv6 address 2001 db8 CAF3::2 /64. IPv6 address FE80::2, a link local. Okay, the next thing is I'm going to do serial 01. So interface serial 11 is there, IPv6 address 2001 DB8 CAF 12:2/64 and IPv6 address FE80:2 link local, and show IPv6 interface brief. Okay, so that's our configuration. Let's go back to PC number 2 and see if we can ping it. No, not that one. So P2, yeah, FE80:2, we chose it. Okay, I need to go back here and change it because I think the gateway I put it 1, it should be 2. That's okay. Okay there. Okay, we have a configuration. We've done this configuration so far here. So what we're gonna do now, we can configure the RIP routing protocol, router RIP configuration mode, advertise our networks. That's what we're gonna do. So click here, I will go to router 1 and config T global configuration mode, router RIP, and advertise the network. So network 172.16.0.0 and network 200.1.1.0 and network 10.0.0.0. That's it. And now we have a version 1 running. So the command C to verify show IP protocols. Right, when I did show IP protocols, we can see that the protocol that we're running is RIP. So routing protocol is RIP. The timers, we can see sending updates every 30 seconds. Next day in 0 seconds, so must be just sent now. Invalid after 180 seconds. Hold down time is 180 seconds. And flush down after 240 seconds. So if it doesn't receive another update in 30 seconds, it's going to keep it in an invalid state, but still on the routing protocol, on the routing table for 180 seconds. Not going to do any updates or anything for that route for another 180 for those 180 seconds, and it's going to flush it after 240 seconds. You can see the default version is send version 1, receive any version 1 and version 2. So on the interface fast Ethernet 0/0, it's sending version 1, but it's receiving both version 1 and 2. On the serial, same thing. And then in the loopback as well, it's sending version 1, but it's receiving both version 1 and version 2. Now that's a problem because there's no router connected to the loopback, or there's no another RIP router connected to fast Ethernet. So those two interfaces, we are just sending updates for no reason. That's where we can do something called passive interface. So we don't need to send updates on those two interfaces. The networks that we are routing for are 10.0.0.0, 172.16.0.0, and 200.1.1.0. Now, the default administrative distance is 120. Okay, so what I'm going to do is go to the RIP. No, we'll do that later. Let's do the router 2 as well. Router 2, show IP interface brief, and we're going to advertise those two networks. So config T, router RIP. When we do it just like this, we are using version 1 RIP. If you want to use version 2, we have to type version 2. But let's do version 1 first. So network 192.168.1.0 and network 10.1.1.0. Now, version 1 is a class full, so you can just do network 10.0.0.0, same. And show IP route, actually show IP protocols. Let's see protocols. Same thing. Protocols, we send it in every 30 seconds, next due in 0 seconds. Again, invalid, same, the timers are the same. We are sending on all of our interfaces version 1. We're receiving version 1 and version 2. Automatic network summarization, it is in effect. Maximum for load balancing, we can have 4 files by default, up to 6. Routing for network 10.0.0.0 and network 192.168.1.0. Gateway, we learned one neighbor, we can see someone, distance 120. The default administrative distance is 130. So show IP route. We can see that we have learned some routes. If you want to see exactly what's happening, you can debug you can see that we are sending the broadcast updates. Okay, now router 2 knows how to get to the loopback interface via neighbor 10.1.1.1 and exit interface is serial 11, and router 1 LAN administrative distance 120 hop 1, and it's via this network's IP address or this neighbor's IP address, and it's through serial 1/1 exit interface. So this PC should be able to communicate with this PC and vice versa. Right, so first thing we need to do is check that R1 knows about those routes. So show IP route. We can see that R1 knows how to get to router 2's LAN as well. Okay, so you can see R1, we are here, run that interface. Show IP route. We can see that there's a network 192.168.1.0, which is this network. We have learned to RIP, administrative distance 120. It's 1 hop away, and it's out of this interface via networks, neighbor's IP address 10.1.1.2, and exit is serial 10. We said that this is 10, yep. Okay, so now I'm going to go to this PC and try and ping this PC. Okay, PC number 1. Do IP config. Yep, we still have the information. So ping 192.168.1.20. PC1 can communicate with the PC number 2. We can do the same thing for PC2. Try and communicate. Ping 172.16.3.10. Yeah, PC2 can talk to PC1 as well. The next thing we're going to do is examine the default RIP settings, which we did. We saw the timers, we saw what interfaces, what networks we're routing from, what interfaces we are sending updates, which kind of protocol we are receiving updates. Enabling RIP version 2. To enable the RIP version 2, all we have to do is go to the routing protocol. So config T, router, RIP, enter, and then type version 2. Done. So now instead of sending the broadcast 255 our updates, we are sending them as a unicast. Do you remember the address? Multicast address 224.0.0.9. So show IP protocols. So now we can see that we are sending updates every 30 seconds. Next, during 3 seconds, we are sending version 2 and receiving version 2. RIP version, the other router, see, show IP protocols, is receiving version 1 and version 2, but it's sending only version 1. Right? So show IP route. Right? After a while, this route will go in the invalid timer. I don't know if you have time to wait for it. I'm going to pause the video. Okay, after waiting a while, I did wait a while, I don't know, about a minute and a half. I was running this command quite often, like quite lots of times, to try and see it, and it actually went down. It says possibly down. It hasn't received an update. So you can see that even though this hasn't received an update, has gone by without receiving an update, now it's put the network in possibly down state. Now if I repeat the command, show IP route, you can see the possibly down. What happens if I try and ping from PC1 again to PC2. There it goes through. You see, the packets are all going through. It's just saying that possibly down, so I'm gonna keep sending packets even though it could be down. Now the reason why is because router 2 is sending updates version 1, and router 1 is receiving updates only version 2. Show IP protocols, so we can see that it's receiving update version 2, so they're not agreeing on the updates. Okay, show IP root now has been removed. The root has actually gone. Okay, so we need to go to router 2 and make it the version 2. Router RIP version 2. Okay, now when we go to router 1, we should see that root come back again after a while. So RIP is not very fast to converge. Here we go, it's really quick actually, just as I said. Okay, so RIP has learned this root. Router 1 has learned this root through RIP 192.168.1.0/24, administrative distance hop 20, hop 1, a neighbor's IP address, exit interface. Now if you want to see a bit more information for that root, we can say show IP root and actually the root. So this one, 192.168.1.0. So you can see the entry for this root on the routing table is known via RIP, distance 120, metric 1, redistributing via RIP, last update from this neighbor on this interface 3 seconds ago. And then routing description 10.1.1.2 from this interface. Metric is 1, traffic share count is 1. Okay, now both of the routers, router 1 and router 2, are doing version 2. Show IP protocols. You can see that it's sending version 2 and it's receiving version 2. Same. Show IP protocols. And it's sending as well router 2 is sending version 2 and it's receiving version 2. The next thing we have to do is disable auto summarization. So if I go to, for example, say router 1, you can see the automatic network summarization is in effect. So we have to disable that. So config T, router RIP, no auto summary. Right, and show IP protocols. Now it says automatic network summarization is not in effect because we disabled that. So we have to do the same for router 2. Router 2 at the moment it says it is on the effect. So config T, router RIP, no auto summary. And then show IP protocols. Protocol. Show IP protocol. You can see that automatic network summarization is not in effect now on router 2. Okay, and one more thing that we have to, configure passive interfaces. If I go again to router 1, you can see that router 1 is sending updates on those 3 interfaces: fast Ethernet 00, loopback 0, and serial 10. I want the updates to actually just go here, not on those 2 interfaces, because it's a waste going on those 2 interfaces. There's no another router connected to it. So I need to go to config T, router RIP, and passive interface FA00. I don't want to send updates on that interface, and I can say passive interface loopback 0 and show IP root, show IP protocols. There. Now you can see that it's routing for these networks, but it's only sending the updates on the serial 1/0, only there. Passive interfaces is fast Ethernet 00 and loopback 0. So it's not sending updates on those 2 interfaces because there's no point. There's no another router connected to it. It's only like internet and this is a client machine. So we just don't want to send updates on the internet, towards the internet. So we do same thing for router 2. Router 2, you can see that it's sending updates on the fast Ethernet, sending updates that way, and it's sending updates this way. But we don't need to send updates that way, so we can disable that. Router RIP, I can say passive interface. I go to fast Ethernet 01 like this, or I can say default. Now default, it will stop sending passive interface. It will do passive interface everywhere. So, but that's a problem because we do want to send updates through this interface. So we have to say no passive interface serial 11, because we do want to send passive updates through that interface. So and show IP protocols. Can't spell it. Always missing. Okay, you can see now they're sending updates through this serial 11 interface. Automatic summarization is not in effect, that's true. Passive interface, you can see all the interfaces are passive. By default, as soon as you say default, it will pick every interface there is on the router, it will make it default. Passive interface default. So you have to go to each individual interface and say no passive interface. If I go to config T, global configuration mode, I enter that interface, the serial, IP RIP, and the question mark. So in here, inside the interface, you can do authentication. So we can authenticate our neighbors. We can set the timers, for example, receive advertisement, send advertisement, triggered updates. So for example, send version, for example, what version do we want to send? Send version 1 or send version 2? We can do both, send 1 and 2. Okay. Receive, what? Receive version, what version we want to receive? 1 and 2 or both. Propagate a default route. For example, R1 has a default route towards the internet or towards the loopback, and then we need to propagate that default route to router 2. So we create a default route towards the internet. So we go to router 1 and config T. To create a default route, create a static default route. So IP route any network, any destination is we're gonna send the loopback 0. Done. And show IP route. Now we can see that we have a gateway gateway of last resort, and it's going to the default route, static route S, and it's got the asterisk. Asterisk stands for candidate for the default route, and it's going to loopback 0. Now what we need to do is propagate this default route to router 2. So if I go to router 2 and I'll do show IP route, we can see the gateway is not set, or last resort is not set. So on the router 1, config T, router RIP, redistribute static. Redistribute static. We can put metric if we want, or that will be just enough. Enter. Now once we redistribute the static, we go to router 2 and run the command again. Now we can see the gateway of last resort is 10.1.1.1, which is router 1, to any network 0.0.0.0. So we learn it through RIP, and this is the candidate default route. Candidate default route. Okay, so administrative distance 120 with hop 1. We could change the hop just to make it maybe less admirable. So we can do no. So I can go left arrow or Control A, go right to the begin and say no. No redistribute static. Say redistribute static and say metric, say 10. So we redistributed our static route, which is the default route. We just manipulated the metric from 1, default of 1, which is going to be, because for 1, we set it to 10. So we go to router 2, we run the commands again. We can see the default route, candidate default route, now has got metric of 10. Okay. Next thing is we're going to configure router NG, RIPng, sorry, Routing Information Protocol, or RIPng and new generation. This is for version 6, advertising IPv6 networks. So if I go to router 1, type enter here, and what I'm going to do is I'm going to advertise version 6. So first thing you do is IPv unicast routing, which we did this before. So, but just remember, this is the first command. As soon as you start IPv6, this is the first command you want to type: IPv6 unicast-routing, because it's not enabled by default. In version 6 or RIPng, it's no more router, RIP and all that. We don't have to do it. We just have to go to the interface. So for example, I go to this interface here. So interface FA00, IPv6, RIP, and then give it a name. What name do you want to? So it says a word, user selected string, identify the RIP process. So what word we want to say? Say RIPng, new generation, and we need to type enable, as we are enabling this protocol. So enable. That's it. It's very, very simple in version 6. So exit, we did that for interface, and then we do it for the second serial interface. So serial 10, IPv6, RIPng, enable. Done. Right. Show IPv6 protocols. When I do show IPv6 protocol, IPv6, we can see the RIPng is enabled, and interfaces serial 10, fast Ethernet 00. Okay, now I'm in router 2. I'm gonna do a same configuration. So config T, IPv6 unicast, we already did it, so we don't have to do this again. Go to the interface, so interface serial 11, IPv6, RIPng, enable. Oh, it says IPv6 routing is not enabled. Okay, so we didn't do it. Exit, IPv6 unicast routing. Okay, interface S11, IPv6, let me repeat that command, enable. Exit, and then interface FA01, IPv6, done. RIPng enabled. End. And show IPv6 protocols. Okay, we can see the v6 routing protocol is RIPng, and its interface is using fast Ethernet 01 and serial 11. Show IPv6 route. You can see that we have learned a route through RIP. The route is 2001 db8 cafe.1 or :1 : 64, which is this route here. Okay, let's do it for router 1. So see if we see any information. Show IPv6 route. Yep, we have learned this route. So now we should PC1, you should be able to ping the other PC2 in version 6. So let's try that. Okay, so ping, what are we doing? 2001 db8 cafe 3 : what was it, 14? I can't remember. 14. Yep, we have a reply. That's all working fine for it as well. Okay, that was the demonstration to configure RIP routing protocol for version 4 and version 6. Concept of a parent-child relationship in a dynamically built routing table. Routes are discussed in terms of ultimate route. An ultimate route is a routing table entry that contains either an next hop IPv4 address or an exit interface. Directly connected, dynamically learned, and local routes are ultimate routes. Then we have a level 1 route. Level 1 route is a route with a subnet mask equal to or less than a classful mask of the network address. Level 1 parent route. Level 1 parent route is a level 1 network route that is subnetted. A parent route can never be an ultimate route. And level 2 child routes. A level 2 child root is a root that is a subnetted of a class full network addresses. Okay, if I go to my router, say I'm going to go to router 1 and run the command show IP root. Now when I do show IP root, I can see that first I have ultimate root. One of the ultimate roots is directly connected roots. For example, this route towards the internet is directly connected and it's got the exit interface, so this is ultimate root. Now I can see one parent root, level 1 parent root. For example, this is a level 1 parent root. You can see this can never be an ultimate root because it doesn't have an exit interface. I can see there is no exit interface. This is a parent root. Level 2 child root is the one that's been subnetted. For example, this is a child root and it's got exit interface as well. So if you remember, ultimate root is the one that has a next hop, either next hop IP address or exit interface. Level 1 root, a level 1 root is a root with the subnet mask equal to or less than a class full of the network address. Parent root, level 1 parent root was a level 1 network root that's subnetted. A parent root can never be ultimate root. And then we have a child root. Child root, they subnetted of a class full network addresses. The reason why we have a level 1 and a level 2 child roots is if the packet comes in and is, for example, if you have a lot of child roots of this parent roots 10 network, for example, the packet is going to try and match the parent network. If there's no match on the parent network, there's no need to try and match the child roots because there's nothing going to be matched. So it's going to move to the next parent root. Thank you very much for watching. We did examine the RIP NG configuration as well. So thank you very much for watching. Please have a look at my other videos and don't forget to subscribe. It's been me, Astrid Krasniqi, showing you CCNA Semester 2 Chapter 7 Dynamic Routing or Routing Dynamically. Bye.